Hi guys, I did not really do a video for energy, therefore I am going to do a quick video for energy. Basically what I want to do here is discuss a problem that I didn't discuss in the class. Okay, so that's my my plan. Now let's see. So we know already kinetic energy Ke 1/2 mv square. Some textbooks use this as K. Potential energy, gravitational potential energy is given by mgh, and that sometimes textbooks use it as U. And the elastic potential energy is given by 1/2 kx square, where k is the spring constant, right? Now there are a couple of things that we need to remember about getting h. Now in order to find h, we have to define zero potential level. Every single time we have to define the zero potential level, all the heights measured in the upward direction as taken, they are taken as positive heights. These are negative heights, and at this point h equals to 0. And similarly, you have to define the equilibrium point when you are looking at the half kx square equation. The x is measured with respect to the equilibrium point. Let's say that you have a mass attached to a spring, and at this point x equals to 0, and the elastic potential energy of this system is 0 because x equals to 0. And the next system I am going to draw it where the spring is extended by a certain amount, and this is your x. Okay, so there the elastic potential energy is given by 1/2 kx square. All these things we discussed in the class last time. Now after that we discussed the mechanical energy. Mechanical energy is the sum of kinetic energy and the potential energy. Now the potential energy has two forms. One is gravitational potential energy, and the other one is the elastic potential energy. If there is no spring, elastic potential energy is out, and the gravitational potential energy is more or less like it's there all the time. However, if a system is not changing its height, the potential energy, the gravitational potential energy gets cancelled out from both sides, mainly because the height, the elevation does not change. And then we discussed conservation of energy, right? So the conservation of energy of like a system, let's talk about a system, like a closed system. In a closed system, energy is conserved. Meaning, if you are, let's say that looking at two objects, and after some time you are looking at the same two objects, and you are looking at the energies. So the energy initial equals to energy final. Or if you are taking a point A and a point B, and as long as the system does not change, energy, the total energy at point A of the system would be the same as the total energy of the system at point B. So you kind of get the idea, right? And then the kinetic energy initial plus the potential energy. Now if I expand this, this would be gravitational potential energy plus the elastic potential energy initial, and then the kinetic energy final plus gravitational potential energy final plus elastic potential energy final. So basically I wrote the whole thing, but as I mentioned earlier, if you do not have a spring attached to the system, these guys don't really play any role. Also, if you have a system where, like, initially you are at a certain level, let's say at this level, this is the system at the initial point, and then the final also, if you have the system at the same level, then the h initial would be equal to h final, depending on where you take the zero potential level, and they actually cause the mgh initial equal to the mgh final. So eventually they will cancel out from both sides of the equation. So when you get to a point problem, we can talk about that. Okay. Now I am going to get a problem that we did not discuss in the class, and let's see how we can do it. Okay, so here we have a problem, and I would like you to pause the video and read the problem and write down the information that we may want at some point. Okay. Now there are a couple of key points here. One I am going to call point A at the top, and then I am going to call this point B. Let me actually write it using blue. This is B, this is A, and the last point over here is C. So the question eventually asks us to find the point H. This is what you are looking for. And then at point A, energy at point A equals to energy at point B. Energy at point B equals to energy at point C. So we can use the conservation of energy 2 times. First, you can write the conservation of energy for A point and B point, and by doing that, our expectation is to find the velocity at this point. Find the velocity at that point, because we already know that going from B to C, that is actually not just a linear motion, it is a projectile motion. And at point C, if I ask you what is the velocity, then some of you may say the velocity is 0, but the answer is incorrect. Y component of the velocity is 0, but the x component velocity would be the same as v cosine theta, because the x component acceleration is 0. As a result of that, initial x component of the velocity would be the same everywhere. In order to remind those, you will have to go back to the previously done questions, or the chapters. It was chapter 4, I believe, the projectile motion. That's where we learned. Now I am looking at the point EA and the point B, and then I am writing down the things that we know. For some reason this tip is a little bit wider. Let's see. Anyway, so the initial velocity at point B equals to 0. V initial equals to 0. That is because the system is starting from 0. That's what the problem says. And H initial equals to big H, and the big H is given to us as 20 meters. So we know the situation at point A. And when you look at point B, V final, we don't know what it is, so it's V. And then H final equals to 0, because this is the level we take as our 0 potential level. So when you use in the total energy at point A and at point B, kinetic energy initial goes away, because V initial is 0, and mgh initial will stay, and there you have kinetic energy final that will stay, and then potential energy term will go away, because that is mgh final, which is 0. So kinetic energy term goes away here, and if I plug the numbers, Hi equals to 20, and the kinetic energy, if I expand it and write it here, that, right? So if I go ahead and plug, remove the m, because it's common in both places, and if I substitute for g, there you will have 9.8 times 20, and cross multiply by 2, there you have v square. And then when you take the square root of that, both sides, you will end up with v square root would be simply v, and there you will have the square root of 2 times 9.8 times 20. Yeah, so I get about 19.8 meter per second when I do the math there, right? So that is not what we want, but you know, we just found out that the speed at point B, or the velocity is 19.8. Now when you look at these point B and C, and when you write the energy conservations again, you will get, now we are looking at the point B and point C. Now here you got to be very careful, guys. Here you have the initial velocity, that's what we found, 19.8 meter per second, and final velocity, we know final velocity equals to 19.8 cosine of 28. Now let me go back to the top slowly and show you that in a projectile motion where the ball is projected in a direction like that, and at the top all what you have is the x component velocity, and the x component velocity, if this angle is 28, we already know from last classes v naught x is v cosine 28, and here you have x component, this is the initial x component, there you have any random x component velocity, and that doesn't change because there is no acceleration pointed along that direction. When there is no acceleration, remember we discussed about cruise control, and the speed of the car in a situation like that, it goes with the same velocity as long as you are on cruise control. So the same way, the x component acceleration is 0, and as a result of that, the velocity at the topmost point is basically the x component velocity. However, at point B we have a velocity v, and that's what we are using. Now you may be wondering how comes that I am using all these things in all different directions, but again remember the kinetic energy, which is a scalar, it is not a vector. So 1/2 mv square, all what matters is the velocity at that point. So 1/2 mv square, all what you need is the, I mean you can call it speed, whatever the speed at applied at that point is all what you need. And then kinetic energy initial is that, and the potential energy initial is next, and potential energy initial is mg h initial. At point B, h initial is still 0, so that term goes away. On the other side you have kinetic energy final plus the potential energy final, and none of them are zeros at this point, so we will have to plug the numbers in. So I'm going to expand these things and write down, and mgh final, and h final in this case is nothing but the height of the ramp, this height, that is what we are looking for. So you may want to discuss this problem, I mean read this problem one more time on your own and do it like, you know, either with me, and maybe watch this video and then do it without me. So let me rewrite the equation. 1/2 m v square 19.8 square and 0, and the other side you have 1/2 m 19.8 cosine 28, that is our new speed at the top, and the square of that, and mgh. Now look at this, we have m common in this term, m common in this term, and m common over there, so I can actually cancel m out because it's common everywhere. I mean, don't ask me whether if there's an m over here, because we are a calculus based class and that is not a proper question, right? I mean, you can put an m if you want, but that's a 0, so it doesn't really matter. Now if you want to simplify this, there you have 1/2 19.8 square, and the other side 1/2, actually it's a 0, it's not okay there, 1/2 19.8 cosine 28 square, and there you have GH. Now everything we know except the H. You can do the simplification and find H, and that is the answer for this question. Now the second part of the question asks you, if he increased his weight by putting on a backpack, would H then be greater, less, or the same? And the answer to that question would be given, or can be given, by looking at this equation. Look at this equation. What happened to M? Whether you use a backpack or not, M gets cancelled out if it is common in both sides. So the answer to part B is it doesn't matter. M cancels out. So nothing actually change. Everything would stay the same. So that's it. 16 minutes, guys. I'm going to stop here. And if you have any questions, please ask me without waiting until the third exam, the final exam.